It's a good-looking hamburger you have there on the front row. I'm glad I ate dinner. The reason I don't have the tie on tonight is that it's our spring break, and I've already gotten a ribbing from Dr. Lowry and Dr. Woods about it, but I don't really care tonight. Where we're going to start this evening is section 20 in your reference manual. It's on page 16-15. And in your notes from last week, I had them numbered as the sessions in your book, and if you'll sort of flip through those notes, you'll find one that's labeled 20 that says pavement design parameters. And that's what we're going to be talking about tonight. And I made a few notes here that I'll go over with you as we go through this procedure. I've got about an hour to cover about a week's worth of lectures, so it'll go pretty quick. If you have questions, stop me and we'll try and get them answered. When we look at pavement design in section 20, the parameters that we're really going to be looking at are things that we need to be able to do is to look at the strengths of the different layers of the pavement. And really those strengths are going to depend on what the quality of the basement soil is underneath that pavement. We're going to need to look at the equivalent axle loadings, or the load that's going to be placed on that pavement. And there we're really talking about having to count the number of trucks that are traveling along that pavement surface and the loads that are on each of the axles of those trucks. We'll also need to be able to predict traffic growth, because typically when we design pavements, we're designing for one-way truck volumes for a 20-year period. So those are the three parameters that we're looking for: layer strengths based on the quality of the soil underneath the pavement, the equivalent axle loadings, which is based on the number of trucks, and then this traffic growth, we're looking at a 20-year design period. Now, I have two overheads that aren't in your notes, if we could, just to show you what we're talking about when we talk about the pavement cross sections. I'm showing a flexible pavement cross section on this particular transparency, and what we have starting from the ground up is the subgrade, or the basement soil. That's the underlying soil we're going to build the pavement on. And then for a flexible pavement, we'll have a subbase, a base, and then finally that top layer will be the asphaltic cement concrete surface. And we're interested in how thick each of those layers need to be. If you look at a cross-section of a rigid pavement, and again this is not in your notes, we have the subgrade, or the basement soil, the subbase, and then the surface, which is a Portland cement concrete slab. Typically it's going to be 9 to 12 inches in depth. Flexible pavements are typically used for higher traffic volumes. Rigid pavements are used for higher traffic volumes because they tend to last longer. Flexible pavements are a little bit cheaper and used for lower traffic volumes. The other slide that's not in your notes, again, we have the wheel loadings that we're looking at for flexible pavement, and then I'll show you for a rigid pavement as well. But at the top of this drawing, that semicircle represents a vehicle's tire on the pavement surface, showing 30 psi, so it's a passenger car tire. And you can see that those downward forces sort of spread out as they move down towards the subgrade that's supporting the pavement surface. And those are the different layers that we just talked about: the surface, the base, the subbase, and then we're designing those thicknesses so that they exert an acceptable pressure on the subgrade there. If you look at the difference between a flexible pavement and a rigid pavement, when we're looking at rigid pavement, we still have our subgrade and our base material, but our surface, that rigid concrete slab, is essentially a beam that's supporting, giving uniform loading all across the the subgrade there. Now if we go back to your notes, one of the things we need to be able to do is to convert our pavement loads to equivalent axle loadings. We can use actual odometer readings where we go out in the field and through some type of counter actually count the number of axles that pass over a particular roadway, and then we can multiply those axle counts by equivalency factors. And there are some appendices in your reference manual for converting axle counts to equivalent axle loadings. In method B, we can convert other equivalent axle loads to 18 kip loads. For example, in this particular equation, if we wanted to convert 12 kip loads to 18 kip loads, we would simply take the number of 12 kip loads divided by 18, and there's an exponent there to raise it to the fourth power. And really what we're doing is increasing those 12 kip loads up to some equivalent number of 18 kip loads. It is a 4 there because the relationship or the force pressure that's exerted down on the pavement, it's not linear, it's an exponential relationship. Another method of converting equivalent axle loads is method C, where you take it from any year, any number of years, and convert it up to the 20-year design life for the pavement. For example, if you had 1 year equivalent axle loading, you'd simply substitute 1 in the denominator of that equation and multiply your equivalent axle load for 1 year times 20, as shown there. Some other methods that can be used, you can approximate your equivalent axle loads based on the number of trucks passing per day. That rather long formula that you see there, let me just go over it real briefly with you. We're converting to 20-year periods, in that 1380 is multiplied by the number of 2-axle trucks that pass the roadway in a day's time period. 3,680 is multiplied by the number of 3-axle trucks, and then you have the other truck constants in there as well. Those constants come from tables. I don't think the tables are in your book, but there are tables that have those, and essentially for AASHTO equations, those would be the numbers that you would use. So you have truck constants multiplied by the number of trucks of different with different axle configurations. Add that equation up and you come up with an equivalent axle load for 20 years. You can convert 5,000 pound equivalent wheel loads to 18 kip loads. That 11.8 in the denominator of the equation is a constant for a 5,000 pound wheel load, just converting different loads to equivalent 18 kips. You can, in method F, convert a design index to a 20-year equivalent axle load. There's tables in your reference manual, table 1613 on page 16 in your manual that you can use to do that. Or you can convert a traffic index to a 20-year equivalent axle load. This last method is what's used in California, where they compute something called a traffic index, and then they can use an equation to convert that traffic index to an equivalent axle load. Now, the third parameter that we talked about was being able to forecast or predict traffic growth, because we're really interested in designing the pavement for a 20-year life. And if we can assume a constant growth rate, we can use our economic equations to compute an equivalent axle load in 20 years. If we know what it is for the first year, which we should be able to get fairly easily, we can use our economic tables and look for the future value of some annual number of equivalent axle loads. We have a constant growth rate of I%, and that's going to accrue over a 20-year period. And you can get that factor from, like I said, your economic tables for different growth percentages. Now, if we look at some of the pavement design procedures, and this is section 21 in your reference manual. I told the group last night that the reference manual has, I think there's 7 different methodologies for designing flexible and rigid pavements. They all go through a step-by-step process. There's a lot of similarities to them, and there's generally an example problem for each one of them in your manual. The most common pavement design procedures are probably those by AASHTO, and we'll use their flexible pavement design as well as their rigid pavement design. There's also a Caltrans method that's used in California for both flexible and rigid pavements, and then there's a couple of others as well. I mentioned AASHTO is the most common, although I've seen questions on the exam using any of these procedures. Might want to go through the steps here, look at the example problems, and again, I think they're fairly self-explanatory. When we look at the first step in flexible pavement design, we're talking about estimating the terminal serviceability index, or P sub T. And that index is really a numerical rating of where we want the road quality to be after 20 years. Okay, 4 to 5 would be a very good roadway surface, very smooth, good rideability. A 1 or a 2 would be very poor quality or poor rideability. And what we're trying to design is to pick some level on that chart where we'd like the roadway to be, or at the time of our first major resurfacing. And generally when we're designing a pavement surface, we're designing it, the terminal serviceability index that we're going to let it get down to is generally 2.5 for most highways. If it's a low volume highway, we might let it get all the way down to 2. Once the roadway is deteriorated to that level, then we would go in with a resurfacing project to try and make it last a longer time. Okay.
Sir?
Yes.
So is there any federal regulation on that? If you were designing, or say you were working for a company and you had to design, is there federal regulation that says if you're designing this type of highway, you can't use such and such a value?
No, there's no federal regulations. Most of the states in their pavement design manuals or pavement design procedures will say they're designing for a serviceability index of 2.5 or 2.0. But I don't think there's no federal standards that say that I'm aware of.
Thank you, sir.
So when we look at that, we estimate what our terminal serviceability index is going to be before our first resurfacing. And there's some charts that you'll see in a few minutes in your notes. You need to read the labels very closely because some of them are for a serviceability index of 2.0. Others are for a serviceability index of 2.5. Step 2 in the procedure, we are going to come up with the equivalent 18 kip single axle loads using one of the procedures that we just went over, and there's a couple of them that you can work with. Step 3, we're going to look at determine what the regional factor, and this is based on where the roadway is going to be built. And what it's trying to take into account is that the load on the pavement surface is going to do more damage to that pavement when the ground is saturated, such as during spring thaw. So if you have areas where you have lots of freeze-thaw cycles, you would have these different R values or regional factors that are shown there. Typically in the continental United States, the range of values you might expect are somewhere between 0.5 and 5.0. So that's the numbers that you see in that table there. We have a regional factor. The next thing we need to estimate is the soil support value. And this is, they use the letter S to denote the soil support value. And it's really trying to take into account what is the quality of the subgrade or the underlying surface that the roadway is going to be built on. And there's different soil groupings that AASHTO has defined. The CTB and BTB in there, that's cement treated base and bituminous treated base, and those would be the ones that would be the best or the highest soil support values or subgrade modulus. And as you go down, the underlying soil is getting worse and worse. For the soil support values, they range theoretically from a low of 0, which would be the bottom soil in that chart, up to a high of 10, which would be for the A1A type of base. Okay. Now what you need to do is to correlate this soil support value S with some other known soil property, such as the California bearing ratio, or there's a couple of other different ways of doing it as well. Now, just for example, in Appendix A in your reference manual, there's a chart or a table that you can use to convert your California bearing ratio values to some subgrade modulus or soil support value. And for example, in this particular chart, if you knew that your soil had a California bearing ratio value of 12.0, you would simply project that line vertically upward until you intersected the average curve, and then go over to the left, and you'd read a subgrade modulus of approximately 210, 212 psi. You go back to that previous table and get some idea of what your soil support value S should be based on this California bearing ratio reading. Now, there's also, you have appendices B and C in your reference manual, different tables. This particular one, again, knows what your California bearing ratio is, your regional factor, and if you know those two things, then you can get some idea of what your soil support value is for that particular subgrade. The final appendix that with strength parameters and layer strengths is Appendix C. Again, a California R value that if you knew that, then you could convert that to a K value or soil support number. We need to define in step 5 a structural number, and that structural number is based on the terminal serviceability index, the equivalent 18 kip axle loads, the soil support value, and the regional factor. Most of these nomographs that are in your reference manual, they're set up to read from the right to the left. So if you take this particular chart, the first thing that you would know is what your equivalent axle loads are, and that's the second line from the right on that chart. And just let me point out one thing on there. The numbers to the right of that bar are the daily equivalent 18 kip loads. The numbers to the left are the 20-year 18 kip loads. So you can use it for whichever one that you want to, but do pay attention that for the 20-year one, those units are in thousands of repetitions. So there's 3 more zeros that would be shown there as well. Okay. Now, if you take an example where you have 2,000 equivalent axle 18 kip loads for daily equivalent, that 2,000 would be a number on the right there of that middle graph. And let's suppose you have a soil support value of 5.75. You would start on your leftmost axis at 5.75, project up and to the right through that 2,000 daily load, and you would intersect your structural number chart looks like about 4.3 or 4.4 in this particular example. Okay. That middle line is your turning line, because once you get to that point, then you have to turn and project down and to the right through your regional factor. And if we had a regional factor of 0.75, you would read a weighted structural number of 4.2 off the line on the far right of this particular chart. So you start out with a soil support value and equivalent axle loads. You get a structural number, and then you have to adjust that structural number to account for the environmental factors, the regional factors in that particular area. And what you're going to be using in your design is the weighted structural number that's on that far right chart. Just a point of information, if your regional factor is 1, you're going to get the same number on your turning line as you do your weighted structural number line. Those are equivalent as long as your regional factor is 1.0. The next thing that we're going to do is to determine what our different layer thicknesses need to be. And if you look at these thicknesses, you might start at the top. We've got a subbase, a base, and then our surface course. So really we're starting the bottom of the pavement is at the bottom of the layers are at the top of this particular chart here. And you'll notice after each of those components there's a little subscript A sub 3, A sub 2, and A sub 1. And those are constants that we're going to use an equation in a few moments. The numbers to the far right are your strength coefficients for different types of materials you might use in building the pavement. So we pick the material, and then we would, once we pick the material and get the appropriate number from that preceding page, we would write our layer thickness equation. Okay, the T's that you see in this equation, those are the thicknesses in inches of the different layers in the pavement. And the A's that you see in that equation, those are the coefficients, strength coefficients from the preceding page. So for example, if we had a thickness for layer 1 of 2 inches and a strength coefficient of 0.2, it would be 2 times 0.2. We'd simply add up those three products and solve for a structural number for that particular pavement design. Now what we would essentially are going to do is we use this equation to compute a structural number, and we compare it to the structural number that we got from the nomograph a few pages back. The example that we used had a structural number of 4.2, and as long as this equation yields a structural number that's greater than 4.2, then it's adequate to support the loads that we're looking at. If we write an equation that produces a number less than 4.2, then it's not thick enough, and we need to go back and come up with some thicker layers in different places. Now, if you look at the example at the bottom of that page, it's a real simple example. They give us a pavement design there. And if you look right in the middle of the page there, it says that they're building a highway in California that has an R value for the basement soil. That's the subgrade of 10. So that's their strength for their basement soil. And the three layers that they're going to build for this particular pavement are 17 inches of subbase, 12 inches of base, and 8 inches of asphaltic concrete. That particular surface is expected to carry the traffic that's shown there at the bottom of the page. You'll notice the different number of 2, 3, 4, and 5 axle trucks. They're given to you in a daily values, and they're assuming a terminal serviceability index of 2.5. Again, it's not a federal standard, but it's almost all flexible pavements are designed for that 2.5. They would then use equation 1632 to compute the equivalent axle loads, and you'll note that those constants are the same ones that they're multiplied by the number of trucks for each of those axle configurations, and it converts to 18.8 times 10 to the 6th, equivalent 18 kip loads. We're going to choose a soil support value of 1 for all of a regional factor of 1 for all of California, and our soil support value for that value is approximately 3 in step 4. They used Appendix B, the table in Appendix B, to come up with that. If you go to the figure, that nomograph with these values, soil support value of 3 up through your 20-year equivalent axle load of 18.8, you would come up with a structural number of 6. So when you have a regional factor of 1, you don't even go to the weighted structural number. So we need a pavement. Our equation needs to produce a structural number of at least 6. Now if we go to the page that has the strength or layer coefficients, we would find those values for the 3 coefficients of A, plug those numbers into the layer thickness equation, multiplied by the appropriate thicknesses, and we would compute that pavement would have a structural number of 7.07. And we're going to compare the 7.07 to the required structural number in step 5. And since 7.07 is greater than 6, we'd say that pavement has adequate strength. If we'd gone through this problem and computed, like I said, a structural number that was less than 6, we'd have to go back and try some different thicknesses in order to get it up to the necessary values. A couple of things to keep in mind when designing pavements is that there's some minimum thicknesses for these different layers. For asphaltic concrete surfaces, at least a minimum of 2 inches, and that's for constructability. And for bases and sub-bases, we need a minimum depth of about 4 inches. If you look at this particular design, it exceeds all of those minimums. Would like to point out in your notes there's an example problem from an example quiz that gives you some parameters based on the existing flexible pavement that was designed according to AASHTO procedures. A couple of things that just to bring your attention: we've talked about initial structural numbers. This particular example says it was 3.5. The equivalent repetitions, or 18 kip single loads before it would wear out, we have a roadbed soil modulus, a design serviceability loss, and then down at the bottom of this particular description, there's some information about when they're going to overlay, or the first major resurfacing for this particular roadway. And it says that after 9,000 repetitions, the effective structural number is going to be down to 2.6, and that's the point at which they're going to resurface that particular roadway, and they've got some design criteria for the overlay period. Now, just to give you an idea of the types of questions that you might be asked about a problem like that, if you look at this page, it's asking the criteria normally used to determine when a pavement needs to be replaced. If you look at that list of things, it's essentially the serviceability is reduced to approximately 2. Those other choices are good guesses, but none of them are correct. If you go to part question 2 there, it says what is the standard load repetition. For pavement design, just remember we convert everything to equivalent 18 kip loads. That's choice B in that list. Part C of that particular problem asks you the remaining life ratio of the flexible pavement just before the overlay is applied. And you use the equation that's shown there, part C. This remaining life ratio is 1 minus this dx there, and that's the number of repetitions before the overlay to the number of repetitions that the pavement is designed to carry. 900 over 1 million, that comes out to be 1 minus 0.9 or 0.1 is the remaining life ratio. And you can go on through the list of questions. I'm not going to go through all of them, but these are the types of questions you might be asked. I might point out one thing on this. They are citing a reference as the AASHTO guide for design of pavement structures. And if you're going to do the traffic part and you don't think there's enough information in your reference manual, that might be a good one to have, but I really think that for most problems there's plenty of material in your reference manual. I might mention before we go too much further, this terminal serviceability index is really a scheme or a strategy to sort of base it on what people would feel or what people would expect a pavement surface rideability to be. And this 2 or 2.5, this number that they sort of magically choose, is at a level where about 85% of the people would be happy with the roadway surface, and about 15% of the people would think that it's too rough and needs to be repaired. You can actually go out and measure what a roadway's terminal serviceability index is. You go out and measure such things as the depth of the rutting on the pavement surface, the number of cracks, the number of patches, plug all those things into an equation and come up with a terminal serviceability. Now, a second method of flexible pavement design is the Caltrans pavement design procedure. A lot of similarities, but there are also some differences. And the second most widely used procedure. Step 1 is determine the 18 kip equivalent axle loads for the pavement surface using some of the procedures from earlier in the reference manual. California uses a traffic index, or a T sub I, in a lot of their design procedures. And there's an equation for calculating T sub I that's given there in your notes. 9 times the equivalent axle loads divided by 10 to the 6th, and then that whole equation is raised to the 0.119 power. Okay. Step 3 is to choose a base material, or the strength of the underlying subgrade, or underlying base. The most typical value that's used for base material is an aggregate base that has an R value equal to 78. Okay. So once you've chosen your base material and you know what your R value is, then you would calculate what's called your total gravel equivalent, G sub E. And there's an equation for calculating G sub E there in your notes. Uses the traffic index, which you calculated in step 2, and this R factor, which comes from the base material that you've chosen. Again, typical value, or most common value for R, is 78. You would then calculate your layer thickness for your base material, and that layer thickness, using equation number 5, we have our gravel equivalent from step 4 divided by gravel equivalent factor, which comes from table 1618 in your reference manual. And that equivalent factor is based on your traffic index and tries to take into account the different types of traffic, cars, trucks, and buses, and then makes adjustments to that gravel equivalent. So we've selected a base material and a thickness. Now we want to select a sub-base material. If you look here at your sub-base material, it's based on what percent of the material will pass through a number 4 sieve. And you'll note the far right of that table are some R values for different classes of material. Those values are 40, 50, and 60. Remember, for your sub-base, the typical value is 78. So now we can determine the thickness of our base and the thickness of our sub-base, and we're going to use the same equations that we used for computing the thickness of our sub-base that we used for computing the thickness of our base. So the equations on the far right of this, same equations that we used on the previous page. Now there's a pretty good example in your notes, example 16.6, should say in your reference manual. It starts on page 1621 and goes through the whole procedure that Caltrans uses. So you might make a note there in your notes, example 16.6 on page 1621. The Asphalt Institute Flexible Pavement Design, probably the easiest one of the 3 procedures to use, because everything sort of defaults to a table lookup type of design. It's easy to use, but it's probably the least common way of designing flexible pavement. Starts out just as the others do, with determining a 20-year 18 kip equivalent axle load. You're going to convert that easel to some traffic class, and there's a table in your manual, table 1620, that tells you the appropriate traffic class for the and it depends on the type of street or highway that you're designing. Parking lot has is type 1, traffic class 1. When you get into freeways, the more traffic they carry, the heavier the loads, the higher the traffic class is going to be. You would classify the subgrade soil based on the table that you see there in the middle of that page. Look at California bearing ratios and equivalent R values for that, and you would then go to step 4 and choose your base and your sub-base materials. Once you've done that, you would simply design the pavement by using table 1622 or 1623, and those happen to be on pages 1623 and 1624 in your reference manual. Those of you that have your reference manual, if you'll look on page 1623, you'll note that the first column says subgrade class, and then you have pavement section. That's your different layers, how thick your surface is going to be, how thick your base is going to be, the different traffic classifications, that's the replications or loading that you're going to have. It actually gives you the thickness in inches that you need for that particular pavement design. So essentially it's a very easy procedure to use, because you simply use table 1622 or 1623. And you look up your thicknesses in that particular table. Now just a bit of a review on 24. Concrete pavements or rigid pavements. We have the Portland concrete slab, which is on top. We have the sub-base, which is underneath, and you'll notice the basement soil or the subgrade. It may have a cement-treated base, it may not. You'll also notice from this drawing something we're going to talk about in a minute. This is a cross-section. Cars would be going into this particular slide, but notice that the roadway is sloping from the center outward. and that's for drainage. We'll talk about that in a few minutes. AASHTO's rigid pavement design procedure, they're going same types of steps, select a terminal serviceability index, and again they're going to use 2.5 for most highways. They would only use the 2 for low volume highways. Determine a 20-year 18 kip equivalent axle load, select some sub-base material, determine the modulus of subgrade reaction for that material, its modulus of elasticity, and that's typically based on static compression test of the concrete, and then what the allowable working stress is going to be for that slab. M sub R is the modulus of rupture, or the 28-day flexural strength of the concrete, and F sub S in the denominator there is a factor of safety. Okay, so there is a safety factor in, and it's generally the safety factor they use for concrete or rigid pavements is 1.33. Once that you know those things, you would go to the chart at the bottom of page 1625 in your reference manual, or reading the slab thickness from figure 1614. And it says it's a design chart for a terminal serviceability index of 2.5. You know your equivalent loadings, you know what your working stress is, you come up to your turning line and go down, and you would come up with the thickness of the concrete that you would need. Okay. And then it says in step 8 that you check for steel reinforcement, and essentially if you come up with a slab depth of 8 inches or less, it says you need to add steel to it for reinforcement. Okay. Second method of rigid pavement design is called the fatigue strength method of design. Same series of steps. I'm not really going to go through all of them because we're beginning to run out of time, but this proposed pavement design in step 1 here, you might just make a note that what you're doing there is to pick the materials that you're going to use and the thickness of those materials. You'll notice there's a factor of safety that's built into this one in step 3, and some other things as well. In your reference manual, there's a series of nomographs that you use in this particular procedure, and in your notes you'll notice it says step 7 is the stress induced in the pavement. Okay. That's the wrong figure in your notes. So if you would, just take and mark through that figure. That goes with the AASHTO pavement design. And what you should be using is figures 1618 and 1619 in your reference manual there. So that is an incorrect figure. And I won't go through the rest of those other than to say that I did leave an equal sign off of the equation there in step 8. Let me move on to section 27 in your manual and in your notes there. And the manual calls it roadway detailing. Just gives you some ideas of some typical design parameters that we try and build into our highways. Lane widths of 12 feet on freeways, and really on most major highways. We use 11 feet in restricted areas. The crown slope or the cross slope, and this is for drainage that I showed you a few minutes ago, from the center line of the roadway out towards the shoulder. And the allowable cross slope depends on what the pavement surface is and how well it drains. The better it drains, the flatter that cross slope can be. Portland cement concrete, a cross slope of about 2%. Something that doesn't drain as well will make it steeper so we can get the water off of the roadway. We don't want to make it too steep, or then it becomes uncomfortable for drivers, and if a driver has to cross over from one side of the road to another, such as passing, we'd like for them be able to do so safely. You'll also notice down towards the bottom of that slide the shoulder widths, typically 6 feet on the right and 5 to 8 feet on the left. We'll use the higher values if we have truck traffic, the lower values if it's primarily passenger cars, and the shoulder cross slope is going to be steeper than for the main lanes, about 5%, and it's sloping away from the median. There's some maximum allowable grades longitudinally along the roadways, 3% for freeways, 6% for other roads, and our design guidelines will allow us to go 2% steeper in mountainous or more rugged terrain. We're limited our grades so that we can trucks can maintain speeds and not have to slow down to crawl speed on our freeways or other major highways. There's some information here about side slopes, right-of-way clearance, median widths, horizontal and vertical clearances. Most of those things there are design guidelines for, and they're decided upon by safety considerations. There is a section in your notes on 28 that talks about pavement joints. When we have rigid concrete pavements, there's different types of joints. There's a figure 1620 in your reference manual illustrates a couple of these, but as we lay these concrete slabs, unless it's a continuous slab, we're going to have construction joints, and how we use those joints to control for contraction, expansion as the temperature heats up and cools down. There is some information about grooving pavements and how you do it and why you do it in terms of advantages and disadvantages. Grooving, we're really cutting grooves longitudinally in the pavement surface. We do it to increase skid resistance on slick pavement surfaces, reduce hydroplaning. It basically gets the water away from the surface of the roadway so that the tires can make contact with it, increases skid resistance and braking capability. When we do this, we're going to reduce the strength of the pavement, so we have to make sure that we have a structurally adequate pavement to begin with, and grooving should be continuous. They also have a tendency to catch on your steel-belted radial tires and make a heck of a noise when you use this particular technique. Geotextiles, again, these are things that are used to their support and filter fabrics and really to stabilize and retain soil, primarily on the roadside and the side slopes, etc. Now, typically, what you will find, the types of questions dealing with these topics are to list advantages and disadvantages of geotextiles, grooving pavements, or something like that. There's a section on subgrade drainage and things that you need to look out for. They're listed on this particular slide where you need to pay particular attention to drainage, where you have high groundwater levels, subgrade soils that become spongy when saturated, seeping water from the underlying terrain, cuts that interrupt natural drainage, or sag curves with a low permeability subgrade. These are just things you need to look out for. Frost damage, something we don't have to worry too much about in College Station, but as you get further north, it does become a problem. There's some techniques for reducing damage from frost. They're listed here, different things that can be done and have been done or tried. We talk about parking design in section 33 in your reference manual. Typical widths of parking stalls are 8 feet. You'll find them slightly wider than that, maybe 9 or 10 feet in market or shopping areas. And they can be as wide as 12 feet when you have a traffic lane adjacent to the parking space. The reason they're wider in market areas is so that shoppers can open their car doors and not ding the car beside them. It's easy to get in and out. They're more likely to come back to that shopping area. You want the wider lanes where you have a traffic lane adjacent to the parking is so that people can open their door and not get hit by passing traffic. Stall lengths are typically 18 feet long, which will fit most vehicles. If you wanted to compute what the parking lot capacity is for a lot or a certain piece of property, you can use that rule of thumb equation there. If you knew what the square footage is of your property, you can divide by 320 to get a rough idea of how many cars you would be able to park in that lot. Now you'll note that 18 feet times 10 foot wide would be 180 square foot. You've got to allow room for people to enter and exit that parking space. There's different ways of parking, angle parking or parallel parking. You can see generally what you'll find in parking design guides is what they call unit parking spaces laid out. Can tell you how many spaces with different angles that you can get for certain size property. And then finally parallel parking at the bottom of that slide. Intersection signaling or traffic signals. There's a manual on uniform traffic control devices that contains a set of warrants or guidelines for when you need to place a traffic signal at a particular intersection. And those guidelines are based on such things as high traffic volumes, interruption of traffic, high crosswalk usage or pedestrians, if you have a school crossing nearby, if you need to regulate speed, if you have excessive accidents that can be corrected by traffic signals, those types of things, they actually give numbers that tell you when you need to put in a traffic signal at a certain location. There's two basic ways for timing traffic signals that are shown on the bottom of that slide, what's called fixed time strategies and on-demand or traffic actuated strategies. The fixed time strategies really are looking at the same time cycle after cycle, day after day, and don't really adjust for changing traffic demands. The traffic actuated uses detectors in the roadway, typically inductive loop detectors, to sense changes in traffic demand and change the signal timings based on the demand at the traffic signal. If you're going to do a signal timing project, there's simple ways of doing it that are outlined in your reference guide. And if you look here at this overhead, you'll see a diagrammatic or a schematic of an intersection in the upper right-hand corner. It has two lanes in each direction as they approach the intersection. You'll notice that there are some numbers there in each of the lanes. Those are the hourly volumes in each of those lanes. And the first step in determining a cycle length is to look at those volumes once you've done a traffic count and determine the highest volume lanes in the X direction and the Y direction. And I'll probably refer to those as north, south, and east, west because that's what I'm used to. Now if you look at those numbers, the highest per lane volume in the north-south direction is that 300 that's circled there at the bottom of the intersection. And the highest per lane volume in the east-west direction is the 800 that's circled there. Once you've determined what those highest volumes are, then you go to step 2 and convert those volumes to passenger car equivalents. Multiply the number of buses by an equivalency factor, the number of trucks by an equivalency factor, and the number of left turning vehicles by an equivalency factor as well. Once you've got the equivalent number of passenger cars, you would go to the table at the bottom of the page and come up with what your cycle length should be. And I circled the wrong number on here. Our highest Y direction volume was 300. Our highest X direction volume was 800. And I should have circled the 90-second cycle from this particular chart. So here's a real quick way to come up with a cycle length for this particular intersection. Once you know the cycle length, the next step is how to proportion that time amongst the two directions. And essentially we do it in a proportioning format. We take the equivalent volume in the x direction divided by the sum of the two equivalent volumes and multiply that by our cycle length of 90 seconds. So if you look at the equation there, the time for the x direction is 300 divided by 1100 multiplied by 90, and the time for the y direction is 800 divided by 1100 multiplied by 90. And those two should add up to 90 seconds, or I made a mistake with my math there. So now we know how much time the east-west and north-south streets get, but we have to do a couple of other things. We need to know how much of that time is going to be yellow or amber. Typically that's picked based on the speed of vehicles that are approaching the intersection. Good rule of thumb is 1 second for every 10 miles per hour of approach speed. And we'll go ranges from 3 to 6 seconds there. We might also want to provide some red clearance time at the end of our yellow of 1 to 2 seconds. Now let's take an example and say we want a 3-second yellow and a 1-second all red. That would mean that for our X street, our east-west street, we'd have 21.5 seconds of green, 3 seconds of yellow, it'd be 20.5 seconds of green, 3 seconds of yellow, and 1 second of all red. And for our north-south street, it would be 61.5 seconds of green, 3 seconds of yellow, and 1 second of all red. And the total time then would be that 90 seconds. So we've got our green, our yellow, and any all red that we want to provide. Now once we've done those calculations, we need to go in step 7 and check to make sure that our times are long enough for pedestrians. Because if we have people that are walking across the street, that light has to stay green long enough for them to get from one curb to the other. And we'd use the equation there in the bottom of that page as a check, where we have a 5-second initial time plus the time to walk across the intersection. And I believe that equation is probably wrong there. We take the width of the intersection and we divide that by a walking speed of 4 feet per second. Okay. So we should take the width of the intersection, that's from curb to curb, divided by a typical walking speed of 4 feet per second, and then add 5 seconds for an initial startup time. For example, if we had an intersection that was 60 feet in width, we divide by 4, we'd come up with 15 seconds of walking time plus 5 seconds initial for a total of 20, and that would mean that our green times would have to be at least 20 seconds in length. And if we go back to the example that I was just using, the first green was 20.5, the second green was 61.5, so they would both satisfy the pedestrian requirements. What would you do if they were less than 20? Well, you'd have to borrow a second or two from the other street, or you'd have to look at going to a longer cycle length in order to get up to those minimum requirements. So just in review, you go through your initial set of calculations. Once you've done that, then you have to check to make sure that you've met pedestrian requirements.
Excuse me, on the cycle times?
Yes.
Do those cycle times change over the period of the day? Does the signal technology support like a morning rush hour with one particular cycle and an afternoon rush hour with a different particular cycle, or?
Yes, even the older fixed time technology, they'll typically have 3 timing plans in an area. One for the morning rush hour, one for the evening rush hour, and then one for the off-peak or the rest of the day. So they'll use different cycle lengths for different times of the day.
Thanks.
Here, I got a quick question. In your step 3, when you determine your cycle length,
yes,
these values on your X and Y are those are your actual E values. correct?
That is correct.
Okay, so, like that 800, you'd convert with member cars, buses, and then you'd look at it there.
That's correct, yes.
All right, thanks.
In this example, I didn't know how many cars and buses, so I just used the numbers from step 1. But if I'd known the cars and buses, I would do exactly as you were saying there. If you go to actuated control, or those that change not only by time of day but from cycle to cycle, the technology gets a little more complicated. Instead of having just a green, a yellow, and a red, we have what's called initial greens and max greens. And those initial greens are based on how many cars we can store between the detector and the stop line. And that's divided by 20 here, which is the average length of a vehicle and the space between it and the next vehicle. And that's the initial period and the vehicle period. That defines the minimum amount of time that approach will get a green. And as long as vehicles keep arriving at the detector, we will keep extending that green until we reach some maximum period for that street. And typically we're looking at 60 seconds of green or 30 to 40 seconds of green for the side street. So there's a minimum amount and a maximum amount of green for each approach. There would also be a yellow period there as well. You notice the last item on that slide says that the green is going to be the smaller of the initial plus the vehicle periods or the maximum period. It could never extend beyond that maximum period. We talk about traffic signals. One of the concepts they introduced in your reference manual is time-space diagrams. There's a time-space diagram in your notes on page 1633, in your reference manual on 1633, and the next page of your notes. Essentially, you're looking at a scale. Typical values are 1 inch equal 100 feet or 1 inch equal 200 feet. You draw your main and intersecting streets to scale. On the time-space diagram, I'll show you in just a minute, that's the vertical lines on the drawing. You come up with an average travel speed along the street, and that's the speed at which vehicles would like to travel. You assume a cycle length, and then you check that cycle length that you've just assumed against the heaviest flow intersection in your system. And you could use that chart for determining cycle length for your heaviest flow intersection. You could then calculate your split times based on equivalent volumes, just like we did in the previous example, and then graphically determine what your offsets are due to travel time between the intersections. Now let me show you a time-space diagram and talk about some of the things we just talked about. Vertical axis is time, horizontal axis is distance. Each of the vertical lines on this diagram represents the center of an intersection along that arterial street. 6 intersections on this arterial. On each of the vertical lines, you'll notice there's a thick black line and a thin black line. Thick black line represents when it's red, the thin line represents when it's green. And the slope of these diagonal lines, I'll lay my pen on my drawing, the slope of that line represents the speed at which people are moving along the street, distance and time. Okay, so the slope of that line represents the speed at which people are moving, and we have to assume a speed or measure a speed out on the street. And you'll notice there's a band of time that I've just put my pencil between, and that's what's called a progression band. If a vehicle can get into that time slot, drive that speed along the street, there'll always be a green light in front of them when they get to the next intersection. And they'll never have to stop unless there's other vehicles stopped in front of them. So we have bands of time going from left to right. We also have bands of time going from right to left in this particular drawing. So we draw our intersections to scale. We have cycles on here. The cycle would be from the start of red at this intersection to the start of the next red. So we have or you could do it from start of green to start of green, but those cycle lengths repeat themselves throughout the system. One requirement for progression along arterial streets is that all of the cycle lengths have to be the same duration, and generally they're limited by the longest, the heaviest volume intersection on the arterial. The one other concept that was mentioned on the preceding page was offset. And offset is defined as the difference in time between the start of green at the first intersection and the start of green at the second intersection. Okay, so we actually, if the green started at time 0 at intersection 1, and this point at the top of my pencil was 10 seconds later, we would say that there's a 10-second offset, or 10-second difference in time between the start of the greens at those two intersections. Essentially, we're trying to base it on a travel time between intersections so that we have a green there when the vehicles arrive at the downstream intersection. And likewise, when we go to intersection 3, now maybe we have a 30-second time difference, and we're going to reference everything back to the first intersection in our system. So this becomes our reference point, or time 0. The start of the green at intersection B is 10 seconds later. The start of green at intersection 3, or intersection C in this diagram, is 30 seconds after the start of green at the first intersection. Remember, we're going to reference everything back to the first intersection. So if this was done to scale, you could actually measure the offsets for each signal in this particular system. And the final thing that I need to cover this afternoon is section 35 in your notes. And just like to point out that we pasted the wrong drawing by the wrong word description there. If you look on the following page, there's a figure that says fully directional interchanges in a drawing. Well, this first one that says a diamond interchange, that's really a picture of a directional interchange. And on the next page, what says a directional interchange is really the picture of the diamond interchange. And if I could start with the diamond interchange, because it's the most common type of interchange, where you have a freeway that you're trying to connect with a cross street. Typically you have ramps, and you'll find a traffic signal at each of the two intersections on the sides of the freeway here. And you find these, the most common type, probably 80% of our interchanges are like this, relatively low traffic volumes. As you sort of move up the scale for cloverleafs and fully directional interchanges, if you have, as your turning volumes or interchange volumes get higher, you can't handle them with traffic signals anymore, you go to these more complicated, sophisticated, they take more space, but they're able to handle higher traffic volumes. Fully directional interchanges, high volume, high speed movements, typically where you have two freeways intersect with one another, you'll find a fully directional interchange. No one has to stop, no one has to slow down unless there's congestion there. So at that point, there's still a couple more notes in the traffic section. Let you go over those on your own.